Yeah, okay, so today we'll go over 6 more devices that utilize PN junction, and they're diode type. They appear to be diode type, but they're used in different kinds of applications. So, but to understand what is really involved, to get a better understanding about electrons flowing and holes flowing, we really should take a look at the band theory, solid state band theory, that explains how electrons and holes, or what the energy of electrons and holes are. Okay, the band theory comes out from the type of physics that we call quantum mechanics. Quantum mechanics views very small particles, such as electrons and even smaller, as some kind of unknown thing that seems to have mass. Okay, they have mass, so that makes them a regular particle in which we can apply regular mechanics to. Okay, classical mechanics. But we also find out that, especially in the case of electrons, they also have wave-like properties. Okay, the wave-like properties make them act like waves. Okay, they don't look at the mass; they have a wavelength. Okay, and they have this energy associated with it. Okay, the reason for that is, let's take an example of what really happens if you consider that. If you consider it as a particle, take the analogy of, let's say that you're in a closed room. Okay, you got 4 walls. Okay, the walls are basically your boundaries. So where you are inside those boundaries, you could be anywhere inside those between those walls. Okay, but you're bound between those walls. All right. So if you become a wave, though, instead of as a particle, if you become a wave, then you don't really have much to say about where your position is. What you do is use statistics. Okay, you use statistics to give you probabilities of where you are within that room. Okay, but the walls of the room now don't become, they're not walls anymore. They're actually energy barriers. Okay, they're energy barriers, and they're high energy barriers. And you inside as a wave are of a lower energy. Okay, but because when you apply wave mechanics or quantum mechanics to it, there you find out that the greatest probability of where you are is right in the middle of the room. However, you have some probability that you can be outside those barriers. Now that's something different. That's something totally different than the classical. Being outside that barrier, okay, it gives you a small probability that you can actually surmount that barrier. That surmounting of that barrier, that's called tunneling, okay? And it actually happens, okay? It actually occurs. Tunneling actually occurs. Electron energy can be outside, can tunnel through that barrier, okay? And then the first item that we will talk about is that tunnel diode, all right? So what the model for that, okay, the model for that comes from an expansion of the quantum mechanic model associated with atoms. Quantum mechanics will basically, when you solve the equation for a hydrogen atom, for example, you come out with that you have a certain number of major shells. Okay, so you got shells 1, 2, 3, and 4, and it builds up. The higher, the further out the shell is, the greater the energy. But quantum mechanics, the solution to quantum mechanics, allows you to have 4 different parameters that specify what that energy is. Okay, these are your quantum numbers that associated with each of the electron that's in one of those shells. Okay, so and the other thing is that there's a principle that says every electron has its own unique series of for the 4 quantum numbers. Okay, so each electron is unique and it has a different set of quantum numbers. Okay, and so that means that within a main shell, actually what happens, you have subshells. So each main shell is made up of subshells. So and you can think of them as having different energy levels within that major category. Okay, so that's good for one atom. But what happens when you have a whole bunch of atoms that come together? When you have a whole bunch of atoms that come together, okay, they interact on their valence electrons, the ones that are the most on the outer shells. They interact with those, and therefore they maintain a different set of quantum numbers. So what happens then is when you create a mass where all these atoms are clung together, you got each of them have 4 close neighbors or more of close neighbors, then you create a whole series of energy levels, okay? And that is called, and though that level, that series of levels is called a band of energy levels. And because it comes from the outermost, that's normally what we call a valence band, because it comes from valence electrons. So you've got energy levels, you have a whole band of energy levels where those electrons are, and each level has its own electron. Okay, but the other thing that the quantum mechanics tells you is, okay, you don't have to stop at your maximum outermost valence band, okay? You actually have energy levels above your valence energy, right? And those also come together to form another band at a higher energy. And that band at the higher energy is called the conduction band. So an electron that's in a valence band, if it has enough energy, it will go into the conduction band and become a free electron and conduct there, leaving behind it a void, which we said is a positive, and it happens to be a hole, and the hole then has a lower energy in the valence band, and that as well can move by different charges. All right, so that's your vision of a valence band, a band model, and you've encountered that when you saw that particular slide, okay, where you've got a conduction band and you've got a valence band, and in between you've got your donor level and your acceptor levels, which contain electrons, or actually donor levels contain electrons, and acceptor levels contain absent bonds, voided bonds, all right? And therefore you get holes from those. So one way to get electrons to flow into from the valence band to the, let's say if you have a valence band to the conduction band, it takes a higher amount of energy. In between the lower part of the conduction band and the highest part of the valence band is an energy level between that, which we call the energy gap. That energy gap essentially is what you need to supply to get an electron to go from the valence band to the conduction band, or to create and therefore create a electron hole pair. All right. So that's called the energy gap, EG. Okay, that's an important parameter. Now, the other thing I didn't mention, but that comes up in the gun effect, is that we said that we create a valence band and a conduction band. Well, truth be known, you actually have more than one. You can have more than one conduction band. Actually, that was part of the thesis that I wrote as a master's thesis when I was in graduate school. I studied this particular semiconducting material, and I found out at higher temperature that the conduction at higher temperatures were a little different than they were at lower temperatures. And it could only be rationalized if there was a second conduction band, okay, a second conduction band. And what the difference was that the electrons that went to the second conduction band had different movement, okay. It moved a little bit more difficultly than they did in the first conduction band. Okay, that's called mobility. Okay, the mobilities were different. Okay, so we take advantage of that in the gun effect, and so that explains, the gun effect can be explained by band theory, and the tunnel diode is explained by the band theory. Yeah, if you don't completely understand, just I can clarify that up if you need to, if you really want to know more. But that's where we'll start. And so we've got 6 things to look at, and we can start now. And give me a call if you need any help or if you don't understand something. Again, we've got the unit questions for you to solve. Okay, I've been getting all of your unit answers and comparing them. We've all been doing pretty good. Okay, no big problems yet. So let's go ahead and don't be afraid to call me.